everyone, welcome to APS Deep Academy, and this is your mentor Swati Joshi. In this class, we will study about bias stabilization. In our earlier class, we completed our discussion on DC load line and we already find the Q point on DC load line. Q point is nothing but the operating point of the transistor from where we can get the maximum output of the transistor. But due to so many variations in transistor parameters and temperature variation also, this Q point is not fixed in DC load line and it is movable in particular manner. So, in particular manner, if this is the position of Q point, it can move here and here also with the effect of temperature. So, bias stabilization is nothing but the maintenance of operating point stable independent of temperature and other transistor parameter is known as bias stabilization. It means we have to make this Q point independent of temperature and independent of other transistor parameter so that the stable condition of this Q point we can achieve. So this whole process is considered as bias stabilization of transistor. Now we will know why we need this stabilization. Okay, the main term here is temperature dependency of IC. We know that ICs are collector current and it is our output current also. And the DC load line or the output characteristic of transistor is directly related with the collector current. So if temperature will increase, this collector current will change, and if this collector current will change, it means output characteristic will change, and this uh, operating point will shift upwards and downwards in DC load line. So it can create a massive change in output of the transistor. Second one is our leakage current. Leakage current is nothing but ICBO, which is a minority charge current and which is generated in the base region. Okay, so this leakage current is nothing but the reverse saturation current, we can say, which we already studied in our earlier topic. It leakage current double for every 10-degree rise in temperature. So if temperature is 50 degrees centigrade and ICBO has some value, when the temperature becomes 60 degrees centigrade, this ICBO double. It means whatever the value of ICBO is, that it is double in that manner. And if this ICBO is doubling, it means the output characteristic or IC will change. Okay. So first one is a temperature dependence of collector current. Second one is leakage current. Okay. Now the third one is transistor gain beta. We know that beta is nothing but the transistor gain, which is nothing but the IC upon IB. Okay, so beta increase with increase in temperature. If beta is changing, it means the operating point will also shift. Now VBE, which is nothing but the base emitter biasing voltage. So base emitter biasing voltage decrease 2.5 millivolt per degree centigrade. Okay, when the temperature will increase per degree centigrade, this VBE will decrease 2.5 millivolt. Okay, now this is also the main reason from where we can get change in collector current and the Q point will shift. And individual variation in transistor. What it means? It means that a the beta of every transistor is different. If a transistor has same number, same size and same configuration, still its beta is different. Why so? Because when we do doping or wafer doping of a particular semiconductor crystal, then the particular width of this base emitter and collector is not appropriate in every configuration. Somewhere it is little bit, doping is little bit high less, and somewhere it is little bit high less. So this can create a difference in two transistors. Either their operation properties, operation and the number are also same, but still their beta is not same. So individual variation in transistor is also there, which can affect change in the beta. Why we consider this individual variation? Suppose a transistor in short circuit, a transistor will stop working and you have to change this transistor to run the particular device. So you will replace this transistor. When you replace this transistor, the another transistor will come and the beta will change. Okay, so here we need the bias stabilization so that this change in beta will not affect the overall output. Here the need of biasing stabilization. Now the last one is our thermal runaway. What is thermal runaway? Thermal runaway is a condition where the temperature increase, the power dissipation of the particular device is at maximum level and the device stopped working due to the high temperature of the particular the high temperature of the particular operating voltages. So this is the condition of thermal runaway due to the high power dissipation. Now these are the few parameters from where the beta can shift in the DC load line. So we have to stabilize this beta so that we can get the maximum output from the transistor. Now we will discuss stability in little more detail. To achieve the better stability, we have the stability factor of transistor. So stability factor is the ratio of change in collector current with respect to leakage current, which is nothing but the ICBO. So stability factor is our change in collector current, which is nothing but the del IC upon del ICBO. So this is our stability factor, change in collector current with respect to the leakage current. Now here the value for stability factor should be in between 1 to 25. Okay. So at maximum we can say it should be 0, but it is not possible because it is electronic device. So ideal condition should be 0, which is not possible. So we consider this condition that it should be in between 1 to 25 or below 25. The output is achievable. After when it increase the value of 25, the output is not received in a particular manner. The output will be changed from the input. So the stability factor, the maximum limit for this stability factor is in between 1 to 25. So 25 stability factor is maximum limit from where we can get the output, but after that the output is distorted. So this is our stability factor for the transistor. Now we will derive the expression for stability. So we consider our basic equation, which is nothing but collector current IC is nothing but beta IB plus 1 plus beta ICBO. We will differentiate this equation with respect to IC and we will make beta constant here. So with respect to IC, if we differentiate, this term will become 1, beta is constant, and this will dIB upon dIC. Similarly here, 1 plus beta, we can consider this term as constant, dICBO upon dIC. Now this term, we can clearly see that this is nothing but 1 upon S. Okay, we already considered the stability factor. So this is our 1 upon S. We can replace this by 1 upon S here. So this is nothing but 1 beta dIB upon dIC plus 1 plus beta upon S. Okay. This term I am considering 1 upon S. So this is 1 plus beta upon S. Now we will solve this equation in terms of stability. So this is 1 minus 1 plus beta upon S, and in another side it is beta dIB upon dIC. If we take the LCM here, then the expression will become like that: S minus 1 plus beta upon S, nothing but beta dIB over dIC. Now if we further solve it, it will become S minus 1 plus beta equal to S beta dIB upon dIC. This S is cross multiply with this. Now we consider all S term in one side. So this is our S term. This will come here and it will become negative beta dIB upon dIC. And this term will become positive. So if we come this here, then it will 1 plus beta. Now here, if we further calculate, we can take S common and this will become 1 minus beta dIB upon dIC, which is nothing but 1 plus beta. So at last, our S is nothing but 1 plus beta upon this whole term. So 1 minus beta dIB upon dIC. So this is the final equation for stability factor. In this class, we already completed our discussion on stability and bias stabilization. So in next class, we will study about biasing of transistor circuits. This is enough for today. We will consider new topics in our new class. Thank you so much.